solve the system of nonlinear equations, and we're allowed to use any method. But notice we actually can't use the elimination method because the second equation does not contain an x squared or a y squared, and the first equation does not contain an xy term. We're only allowed to multiply an equation by a non-zero constant, so we can't use elimination in this example. So we're going to use substitution instead. And we definitely want to solve for one of the variables in the second equation so that we don't generate a plus or a minus when we take the square root of both sides in the first equation. So let's solve for y in the second equation. We'll do that by dividing both sides by x to get y is equal to 3 over x. Then we'll use this as a substitution for y in the first equation so that we get x squared plus y squared is equal to 10, and in for y we're going to plug in 3 over x. So now we've merged both of these criteria into one equation that only contains one variable. So we can solve this equation for the remaining variable, which in this case is x. Let's go ahead and distribute this square into the parentheses. We're allowed to distribute a square over division, so this becomes x squared plus 9 divided by x squared is equal to 10. And this makes it a little easier to see that what we have now is a rational equation, and we solve those by multiplying both sides by the LCD. The LCD in this particular case is going to be x squared, so we're going to multiply both sides by x squared over 1. X squared times x squared is x to the 4th power. X squared times 9 divided by x squared is just going to be 9. And x squared times 10 is going to be 10x squared. Now what we have is an equation in quadratic form. And we solve that by letting u be equal to the variable expression whose square is also in the problem. So we'll let u be equal to x squared, and then we'll replace x to the 4th with u squared. So this becomes u squared plus 9 is equal to 10u. Now that it's a true quadratic, we're going to set this equal to 0 and solve for u. So we have u squared minus 10u plus 9 after we subtract 10u from both sides. And this quadratic then factors into u minus 9 times u minus 1. We set each of the factors equal to 0 to get that u is equal to 9 and u is equal to 1. And then from here we want to back substitute using that same substitution, which tells us that if u is equal to 9, then x squared is equal to 9. If u is equal to 1, then x squared is equal to 1, and now we continue to solve for x. So we solve for x by taking the square root of both sides, and when I take the square root of both sides, it comes along with a plus or minus on the constant side. So we end up with x is equal to plus or minus 3, and x is equal to plus or minus 1. Now remember, the solutions to this system are going to be ordered pairs that are the intersections between the two graphs. And what we have currently are 4 different x values, which means that we have 4 different ordered pairs that could be solutions. Now, in order to determine if they actually are solutions, we basically need to plug them back into both of the original equations and make sure that we get the same ordered pair solution in both of them. So let's start with x is equal to 3. When x is equal to 3, we end up with y is equal to 3 divided by 3, which is 1. So in the second equation, the corresponding y value output would be positive 1. So now we just need to verify that 3, 1 is actually an ordered pair solution to the first equation as well. So we have x squared plus y squared is equal to 10. We plug in 3 for x and 1 for y, and we see that this actually is going to work because this is 9 plus 1, which does equal to 10. So this first ordered pair is a solution. Now we need to do the same thing 3 more times. So let's see who the corresponding y value is when x is negative 3. So we'll plug in x is equal to negative 3 into the second equation to see who the corresponding y value is to complete this ordered pair. So we'll have y is equal to 3 divided by negative 3, which is negative 1. So negative 1 completes the ordered pair in the second equation. Let's see if this ordered pair is an ordered pair solution to the first equation by plugging in negative 3 for x and negative 1 for y. And again, we see we get positive 9 plus 1, which is 10. So yes, this ordered pair is also an ordered pair solution. Now let's check x is equal to positive 1. We'll plug x is equal to positive 1 into the second equation to see that y would then be equal to 3. So 1, 3 completes the ordered pair in the second equation. Now we need to see if 1, 3 is also an ordered pair solution to this first equation. So we'll plug 1 in for x and 3 in for y, and we see that we have 1 plus 9, which is still equal to 10, and therefore this is an ordered pair solution to the system. And the last time here, we'll plug in x is equal to -1 to the second equation to get the corresponding y value to complete the ordered pair solution for the second equation. So we get y is equal to -3, and now we need to see if -1, -3 is an ordered pair solution to the first equation. So we plug -1 in for x and -3 in for y, and again we get 1 plus 9 is equal to 10. So yes, this is also an ordered pair solution to the system. So we have 4 solutions to this system of equations. Let's take a quick look at the graph of this system in order to understand where those solutions are. So this first equation is a circle that's centered at the origin with a radius that's the square root of 10, which is approximately equal to 3.2. So this circle comes in somewhere around here. To graph this second equation, again, let's solve it for y so that it's a little bit more recognizable, and we see that y is equal to 3 over x, which is actually a vertical stretch on the 1 over x graph, which is the reciprocal function, and we'll have ordered pairs 1, 3 on this graph. 3, 1 is also an ordered pair solution to this function. -1, -3 we found to be an ordered pair solution to this function, but also the system. And -3, -1. All of these were points on both graphs, and as a reminder, that reciprocal function has a vertical asymptote at x is equal to 0, a horizontal asymptote at y is equal to 0, and this reciprocal function approaches both of these asymptotes and passes through those 2 ordered pairs in the first quadrant, but also in the third quadrant. And from here you can see that we do actually have 4 solutions to this system. There are 4 ordered pairs that are intersections between this circle and that reciprocal function.